Hello everyone. In lab, hopefully you noticed that when you drop something in water, it becomes lighter. Now it doesn't actually become lighter because there's less gravity pulling on it. It still has the same amount of weight, but there is a force from the fluid acting on it. And that arises from here. And you went through this part in the lab, and I want to walk through and make sure we all got similar answers here. So when you suspend an object in a fluid, there's actually pressure acting in all directions all the way around it. But we're simplifying things, and basically we're saying, okay, well, the pressure left and the pressure right, those are going to add up and cancel. But the pressure on the bottom and the pressure on the top, those don't cancel, because remember, pressure depends directly on depth. Pressure is equal to rho g h, and the higher the column of water above it or fluid above it, the greater the pressure is, which means there's greater pressure down here than up here, which means the net force is acting up on this. So is the pressure on the top equal to the pressure on the bottom? No, the pressure on the bottom is greater because it's deeper, and so there's more pressure. Now, write the equations for force at the top and at the bottom in terms of the density of the fluid, the height, the acceleration of gravity, and the area. All right, so right up here I have pressure is equal to rho gh. But remember, pressure is equal to force over area, which means force is equal to pressure times area. So what I'm going to do is I'm going to say, all right, well, force 1, this would be equal to the density of the fluid, which is constant, times the acceleration of gravity, times h, but this is h1, so h1. Force 2, and then times area. And this is the area of this little cylinder. And then F2 is rho GH2, also times area. Now, this part right here, this third step, there's a lot of simplification we're going to do right here. It says the difference between the force at the top and the bottom of the object gives rise to the buoyant force. Since there's a greater force up than down, this appears lighter because the water supports some of the weight. To find the buoyant force, we're going to take F1 away from F2 because that'll give us the net force from the fluid, which is called the buoyant force. So I have F2, which is rho GH2 times A, minus F1, which is rho GH1 times A. Now this is where things get a little bit interesting, because what we have is, if we simplify this, I have rho GA times H2 minus H1. But H2 minus H1 gives me the height of this little block, which means I have the area of that block times the height of that block, which is really the volume of that block. So rho G A times H is V. Now remember, rho is density, and density is mass over volume. So what I really have now is mass over volume, and this is the density of the fluid, remember, but the volume of this object and the volume of the fluid, they're the same because they occupy the same spot. So mass over volume, and this is of the fluid, times G times V. Well, this volume cancels that volume, and so what I have is the mass of the fluid times the acceleration due to gravity. When you take a mass times the acceleration due to gravity, you get weight, right? So this is actually the weight of the displaced fluid. Okay? Now it says copy our final equation down in the box. The equation for Archimedes' principle really is the buoyant force, FB, is equal to the mass of the displaced fluid, that's what that little f is telling me, times the acceleration due to gravity. It has everything to do with the fluid and not anything to do with the object that's in it. Okay? When objects float, it just means that they are less dense than the fluid they're in. And there's an example of that in this lab that you guys will get through it. This is the word version of Archimedes' principle. It says that the buoyant force that a fluid exerts on an object is equal to the weight of the fluid displaced by the object. This is that same thing in equation form.